and the different wear results when different rules are applied at different times with introduction reading. So first, I will be sharing a quick introduction regarding our Pinundis wear tester, and then I will be discussing the parts and the process on how to operate our machine. Lastly, I will be conducting a short activity that is included in our laboratory manual, and I will run through the procedures and safety precautions with you. For our brief introduction, I would like to check if you are familiar with the word tribology. What comes into your mind when you hear the word tribology? Um, Tribology is actually the study of friction, wear, and lubrication. The reason as to why it is significant is because tribology is the science and engineering of interacting surface in relative motion. Being familiar and knowing how friction, wear, and lubrication can affect each other and the material is important in choosing the kind or type of material to use in different application. Being able to identify the most efficient pair of material or metal by knowing its wear coefficient can actually help us prolong the life of the machine that we are trying to create or build. Our wear tester consists of more than 25 major and minor parts, but I will only show you the parts that is important on the operation of the machine. One of the most important part of our machine is the HMI, or the Human Machine Interface. This is where we input the data needed to operate the machine in a controlled setup. Facing the HMI on the right side, you will see the main switch, the drain valve, and the power cable. And besides the HMI, you will see the emergency stop button, and below this is the indicator lights. The top part of the machine contains the lever arm. This is where you place the weights and the pin. You can also find this on this area. For the step-by-step process on how to operate our machine,
I will read the procedure listed on the activity sheet while showing you the part of the machine in use. Start with calibration. Adjust the level foot and use the level gauge to calibrate if the frame is parallel with the ground. And then, use the level gauge again to calibrate the lever arm with counterweight to check equilibrium. And then, you have to use the dial indicator to calibrate the uniformity of the rotation of the disc. We can now start by measuring the dimension or weight of the pin and make sure to keep a record of it. Next is to lock the pin specimen on the lever arm. You have to make sure to lock it tightly. Next is to apply loads on the pin by putting it on top of the lever arm where the pin is held. A metal rod is attached to secure the weights in place. If you are going to use a lubricant for testing, you have to make sure to close the drain valve before pouring the lubricant on the disc. Make sure to pour the lubricant until it is slightly above the top surface of the disc. If you are using a lubricant, make sure to put on the disc lid before you start the testing. This will make sure that the lubricant will not spill once the disc rotates. Make sure to switch on the circuit breaker and flip the main switch to turn on the wear tester. You will notice that the indicator lights are blinking. This is an indication that the machine is ready to operate. Press the reset button to refresh the program and click the initialize button to set up a new testing. This will bring the actuator up to support the lever arm. We can now input the data needed to start the activity. The data needed are the force, hardness, diameter, initial length, motor speed, wear circumference, which in our case is 80 pi or 251.33. Continue the experiment until the data in the table are complete. After the testing, you can now remove the weight and the pin. After the pin is removed, you need to remeasure the specimen's weight or dimension to compute for the volume lost. Please make sure that you have a proper record of the results of the experiment. Analyze and compute the wear coefficient and wear rate. After the operation, you may now remove the weights to take off the pin from the lever arm. To take off the pin, you have to loosen the screw first. Once the pin is removed, wipe it with a clean cloth to remove the excess lubricant. You can now remeasure the dimensions of the pin. And then, wipe the disc as well to remove the remaining lubricant. You can also use a solvent like acetone to remove the remaining lubricants. Once the operation is complete, you have to make sure to turn off the machine. Note that if the machine will not be used for a number of semesters, remember to lubricate the disc to avoid oxidation. After the testing, make sure to cover the disc using the lid provided. You also have to make sure that the top of the machine is free from any materials like weights and other tools and accessories. For the first activity, we will be using an aluminum pin and different speed and load to generate the volume loss, wear rate, and wear coefficient. For the second activity, we will be using an aluminum pin with different types of lubricant to generate volume loss, wear rate, and wear coefficient. To generate a volume loss of 36.90 millimeter cube, we will be using the equation of initial mass minus final mass divided by density. To generate a wear rate of 4.0783 times 10 raised to negative 6 millimeter cube by millimeter, we will be using the equation of volume loss divided by sliding distance. To generate a wear coefficient of 6.8107 times 10 raised to negative 4, we will be using the equation of volume loss multiplied by hardness divided by sliding distance. After the results was generated and compiled, based on the data during the load and speed test, we noticed that at 20 Newton load, volume loss is greater than 10 Newton load as well as the wear rate. However, the wear coefficient decreases when the load is increased. When we compare 10 Newton at 100 RPM to 10 Newton 600 RPM, the test with greater RPM result to greater volume lost. Unfortunately, during the 20 Newton at 100 RPM test, the motor was unable to withstand the load, therefore, the test was invalid. After the result for the second activity was generated and compiled, based on the data during the lubricant test, we can compare the dry test, oil test, and grease test under 20 Newton 600 RPM. We notice that the volume loss in dry test is greater than the result with grease and oil, as well as the result for the wear rate and wear coefficient. However, the result from the test with oil is an indication that the oil is an effective lubricant to eliminate wear. Therefore, we conclude that greater loads and speed contribute greater wear on the material. For lubricants, specimen submerged in oil generates lesser results than grease due to centrifugal force. The grease was dissipated away from the disc over time. Thus, lubrication was less effective. Therefore, we conclude that greater loads and speed contribute greater wear on a material. For lubricants, specimen submerged in oil generates lesser results than grease due to centrifugal force. The grease was dissipated away from the disc over time. Thus, lubrication was less effective.